Okay, hi. Today we're gonna summarize of the doping of the fabrication technology. The doping is have two ways of the fundamental process. First is the diffusion, and second is the ion implantation. The diffusion is used in the summer doping. It used the summer energy. It related with the heat. And ion implantation is accelerating this ion electronically to the direct into the surface of the silicon. And you can see the diffusion. First step is the pre-deposition. Pre-deposition is literally pre-deposited what we want to dope the dopant atom into the surface of the semiconductor. And step 2 is make these dopant atom in the surface is through in the substrate. And in these steps, it make a dope the substrate. This diffusion system is there's a three type of the source: solid and liquid and gas. This diffusion process is mathematic. We can follow this the first law and second law, and we can learn about this diffusion equation. Its meaning of the so at before the beyond the diffusion equation, it makes a concentration equation. This important thing is pretty important in the DT factor. D is the diffusion coefficient and T is the time. How diffusion is where and how much time you give is an important factor. So we can simulate with the Excel of this equation. And we can see the figure of the pre-deposition and drop-in. Pre-deposition in this is the surface of the semiconductor. So we can deposit the dopant atom in here, and we can make a DT factor. We give the more and more it diffuses into the substrate. And surface concentration is same, but we we give them summer energy, and it makes drive in the dopant atom. First, the lowest DT factor, it have a surface concentration is too high and other atom is here. And we give the more and more DT factor, it gives the more deep into the drive in the substrate. So it reduces the surface concentration. Is this more depth concentration? So this is a more important and pretty important part, the summer budget. The summer budget is it needed in whole entire fabrication technology? Summer budget is the first step. If we can see the step 1 and step 2, there's something we make it under the 80 degrees. And second step is need to 1000 degree. This makes a breakdown before we can reproduce it thing. So the summer budget is so important to whole entire process and evaluating other processing, considering their summer budget. And step 2, we can step when diffusion, and step 2 is drive in. We need the summer energy and how we can give the summer energy. It's called the annealing. Annealing use the furnace, and other annealing is used the lamp, halogen lamps, because the furnace is the have more time to create the summer energy what we wanted, and it has a many time, and this cooling down time is just too high. So the heat remain in the vapor, make other doped, and this is more or less control. So we should have to repeat it to the summer energy giving time. So reduce the time. It makes a cooling down time is just equally reduced. So we can control the dove is easily, but this has not a short, effectively short. So we can use the laser. Laser is the most extremely short time to control. So giving the energy and reducing energy time is so short, extremely short. So we can use this, make a shallow junction. Shallow junction is the means it's very shallow junction, not a deep. So you can see the laser annealing, there's a point of the time. We can give the laser, its temperature is too high in the first time, and it's also down in the first time in the same spot. It makes a spot to the spot. So this annealing is used in many other process, not in Dolphin. It's giving the vapor and semiconductor and summer energy. It means it works as a different ways. So there has a doping process. It's a shallow doping and heavy doping is its relation is trade-off. So it can have reached down at the same time. So when we scaling down, when we make a nanoscale transistor, we should have to series resistance. There is a series resistance is occur, these are parasitic, what we don't want it. So we can reduce these things. These resistance make a gate current and gate on off state. Its influence is not good effect. So through this problem, we can see the limits of the summer dolphin. So we use this the ion implantation. Also, it has a not a good thing, but it can through over the summer limit, summer dolphins limit. First is it is by the electronical control. So its control is so precise. The precise control, it makes it more easier to make a shallow junction, and the control is easy. It also means has a uniformity of the dot in the vapor. And also this is expensive. Yeah, and its mechanism is accelerating the ions into the direct into the surface of the semiconductor. So this is crash and collapse in here, and their lattice is damaged. And this damage make an amorphization, amorphization, and other is channeling and surface etching. Problem is occurs. So this ion implantation mechanism, there's a source, and we select what we want the ion, and we can accelerate the ion and control their direction and into the vapor. The ion source, it makes by the filaments of the plasma. We use the plasma is giving the many energy and temperature. It makes a short time, and we focus. This is the point after the plasma and this ion source. It has other many ions is produced. This ion have a different mass. This is the point. So you can select these particle and ions. How we select these things, we give them the Lorentz force, and they have a different mass. The more heavier going to this, and more lighter going to down. So we can select what we wanted. And these are vertically and horizontally control the direction of the ion. Okay, this the mechanism of the ion implantation. So we make it this implantation, make a mathematical model for the implantation. You can see this impurity concentration. It means is ion implantation. Is this follow the Gauss figures? So the projected range and standard deviation is important. This is why important is when we implant these ions, the ion is going down to the Si2. This is the hard mask. And this position is what we want to adopt it. And this is what we don't want to adopt it. And the ion is have a area into this area is concentrated too high. So it makes this graph. And this time there's this spot is what we don't want to adopt it, but because it's happening, and we should have to reduce this. So we can this follow equation. The x0 is the silicon dioxide depth, and we choose this x0 is preferred to prevent to this concentration. Is concentration machine lower. And this graph is have 4 times of the ion implantation. This ion implantation is good. So totally have a doping profile is here. And this means there's 4 times of the controlling of this doping profile. So easier and precise dope junction we can make. And there's has a problem. The channeling problem is a structural effect problem. So we can use the tilt angle, so we can solve this problem. Oh, but we solve this way. There have other problem is happening. It's a shadowing effect. Shadowing effect is we angling the vapor. They have a shadowing areas may happen. The shadowing area is not doped because they have a not impurity and other things. It is empty space. So this is about the electrical damage. It makes the amorphous state. It makes the silicon is a poly to the amorphous. So we should recover this. We use this annealing process and advanced doping. So we reduce the electrical damage. We can use the hot plate before the substrate, and it makes the lattice is more flexible and it works in to reduce the damage. So reduce the damage after the ion implantation. It has a see the amorphous stage, and after the annealing, it makes a poly and or silicon stage. Okay, this is the important thing. It used the plasma doping. Why we use this process? We can see there's a chemical predeposition into the plasma. They have a uniformity of the thermal energy, and this is the so good advantage of the process. So what we call this conformal. So we use many time in this process in this way. So thank you for my summarization.